Before we travel out into the vastness of the universe, take a moment to simply let go of the day you have just lived. The emails, the errands, the lingering conversations, the quiet worries, and the endless planning for tomorrow, all of that can wait. Imagine taking every thought that feels heavy or urgent and placing it gently in a box beside your bed. You can always pick it back up tomorrow if you need to, but for tonight, you are off the clock. Right now, there is nothing you need to solve, nothing you need to fix, and nowhere else you need to be. Settle into the space around you. Notice the weight of your body supported by the mattress, completely held and entirely safe. Let your shoulders drop away from your ears. Unclench your jaw. Allow your breathing to find a slow, steady, effortless rhythm, the kind of breathing that happens entirely on its own, rising and falling like a calm ocean wave. With every exhale, feel yourself sinking just a fraction of an inch deeper into comfort. Now, keeping your eyes closed, I want you to build a place in your mind. Picture yourself stepping out of your front door, but instead of your usual neighborhood, you find yourself walking into a wide, open landscape, miles and miles away from the bright, artificial glow of city lights. Perhaps it is a high, grassy hill where the wind barely whispers, or a quiet beach where the sand is cool beneath you, or a vast desert floor stretching out flat in every direction. The air here is crisp, clean, and perfectly still. Imagine the sun has just slipped below the horizon. The sky is no longer blue, but it is not yet completely dark. It holds that deep, bruised color of twilight, a gradient of rich violet, fading into a profound, dark indigo directly above you. As you watch, the very last traces of daylight bleed away. And there, emerging through the deepening blue, is the very first point of light. It is usually a planet, like Venus or Jupiter, shining steady and bright, a solitary diamond resting on velvet. As the sky transitions from deep indigo to true pitch black, the rest of the universe begins to reveal itself. It doesn't happen all at once. The stars fade in slowly, one by one, then 10 by 10, until the entire canopy above you is scattered with countless points of cool, distant light. Some are piercingly bright and seem to flicker or twinkle slightly in the atmosphere. Others are so incredibly faint that you can only see them out of the corner of your eye, disappearing if you try to look at them directly. There is a profound, comforting silence in this mental landscape. Looking up at a sky like this, untouched by light pollution, you are participating in the oldest shared experience in human history. For thousands upon thousands of years, humans have stood exactly where you are in your mind right now. Long before the invention of telescopes, before the concepts of physics or mathematics were formalized, our ancestors stood in the cool night air, tilted their heads back, and felt the exact same sense of awe that washes over you. They looked at this seemingly chaotic scattering of light and instinctively did what the human mind does best. They searched for patterns. They drew imaginary lines from dot to dot, creating the outlines of hunters, bears, winged horses, and mythical heroes. These constellations became a permanent, spinning storybook painted on the ceiling of the world. But the sky was more than just stories. It was a vital tool, a celestial clock and calendar. Ancient farmers watched for the rise of specific star clusters to know exactly when the frost was safely past and it was time to plant their seeds. Mariners steered fragile wooden ships across vast, terrifying, featureless oceans, navigating safely back to their homes by trusting their lives to the steady, reliable positions of these very same stars. When you look up, you are intimately connected to every person who has ever lived. The sky you are picturing in your mind is the exact same sky that guided ancient explorers, the exact same sky that poets and philosophers gazed upon when they wondered about our place in the cosmos. And there is something deeply soothing about the sheer scale of it all. In our daily lives, our problems can feel overwhelming. A stressful meeting, an unexpected bill, a difficult relationship, these things naturally command our attention and feel massive, because to us, they are. But when you mentally step out under a canopy of millions of stars, your perspective gently shifts. The universe is unimaginably vast, and in the face of that breathtaking scale, the day-to-day worries shrink down to their proper size. It is not that your life doesn't matter. It is that the universe is large enough to hold all of it effortlessly. There is a great comfort in realizing that the cosmos carries on, silent and majestic, entirely undisturbed by the trivial anxieties of our modern world. Tonight, we are going to explore that vastness together. We will build an understanding of the universe, piece by piece, traveling from our own quiet Earth out to the very edges of space. We won't use complex jargon or confusing numbers. Instead, we will use our imagination, building concepts from the ground up, linking the mysteries of the cosmos to the simple, everyday things you already know. Think of me as a friend walking beside you in the dark, gently pointing out the landmarks along the way. As we prepare to leave the ground and venture upward, remember that there is no rush. We have all the time in the world, and space is endlessly patient. You can let the words wash over you, absorbing what feels interesting and letting go of whatever you choose. If you drift off to sleep halfway through our journey, that is perfectly fine. The stars will still be here, waiting quietly in the dark whenever you return to them. So, take one more deep, slow breath in your mental landscape. Feel the cool air fill your lungs, and as you exhale, feel your focus settle completely on the magnificent canopy above you. And with that understanding quietly in place, we're naturally led to ask how this grand display above us actually moves. If you were to stay out in that quiet, dark field we imagined, lying on a blanket in the cool grass, and simply watch the sky for hours, you would notice something profound. The sky above you is not a static painting. It is in constant, sweeping motion. Very slowly, stars emerge from the eastern horizon, climbing higher into the dark vault of the sky as the hours pass. They trace long, graceful arcs directly over your head, and eventually, if you watch them long enough, they will sink and disappear below the western horizon. It is the exact same path the sun takes during the day, just replaced by a million glittering points of light at night. There is a beautifully rhythmic, almost mechanical precision to this movement. If you turn your head to look toward the north, you might notice that the entire sky seems to be turning around one single, quiet anchor, a faint star that never seems to move, while all the others wheel around it like a colossal, silent carousel. For a very long time, humanity trusted exactly what their eyes told them. They believed the Earth was entirely still, fixed immovably at the center of everything, and that the vast sphere of the universe was rotating around us. It is a completely logical conclusion to draw when you are standing on solid ground. Your senses tell you that you are stationary, and therefore the sky must be what is moving. But as you might already have a sense of from your own experience in the modern world, sometimes the movement we perceive belongs entirely to us, rather than the things we are watching. Imagine, for a moment, that you are sitting on a perfectly smooth, silent passenger train, stopped at a station late at night. You are relaxing in your seat, the cabin is dimly lit, and it is perfectly quiet. Out your window, you see another train resting on the adjacent track. Suddenly, you feel a gentle gliding sensation, and the train outside your window begins to slide backward. For a split second, your brain is entirely convinced that your train is moving forward. It feels undeniably real, but then you glance past the other train and see the station platform, and you realize you haven't moved an inch. It was the other train rolling forward that created the illusion. Or perhaps you have experienced this behind the wheel of a car. You are sitting at a red light, and the large truck next to you slowly begins to roll forward. For a terrifying, fleeting moment, your body tells you that you are rolling backward, and you instinctively press your foot harder on the brake pedal. Our senses can easily be tricked when there is no wind, no jarring vibration, and no clear frame of reference to guide them. The illusion of movement is a powerful thing. Earth is our silent train. We are resting on a massive sphere made of millions of cubic miles of solid rock, iron, and deep, heavy oceans. And this colossal sphere is spinning steadily on its axis. You can picture that axis as a perfectly straight, invisible line drawn straight down through the planet. It enters at the freezing ice of the North Pole, cuts all the way through the molten iron core deep underground, and exits at the South Pole. Every single day, over the course of exactly 24 hours, the Earth completes one full, majestic turn around this invisible line. As the Earth turns, it carries us along with it. When the patch of land you are resting on turns to face toward the sun, you experience the bright, waking hours of day. And as the planet continues its endless, rolling rotation, turning your side of the world away from the sun's glare, you are carried into the shadow of the Earth itself. That shadow is what we call night. The stars are not moving past us. We are simply rolling over to look at them. It is a tremendous amount of physical movement. If you are near the middle of the planet, you are moving incredibly fast just by sitting still. But you feel absolutely none of it. Why is that? Why doesn't the sheer speed of this planetary rotation create a roaring wind or throw us off our feet? The answer lies in two beautifully simple realities of our world. First, there is gravity, drawing you so firmly and reliably toward the center of the Earth that your body simply accepts it as the default state of existence. But the second reason is even more elegant: constant velocity. Think about being on a commercial airplane, cruising smoothly at a high altitude. Once the plane reaches its cruising speed, if you close the window shade, you completely lose the sensation of moving forward. You can pour a cup of hot coffee, set it on the small tray table in front of you, and the dark liquid rests perfectly flat, entirely undisturbed by the fact that you are traveling hundreds of miles an hour. You only ever feel changes in movement: the sudden acceleration of takeoff, the braking deceleration of landing, or the jarring bump of turbulence. But as long as the speed is perfectly steady, movement feels exactly like standing still. The Earth's rotation is the ultimate smooth flight. It doesn't speed up and it doesn't slow down. It turns with an ancient, unwavering consistency. There is no turbulence. Furthermore, the thick blanket of our atmosphere, all the air we breathe, the clouds that drift above us, and the winds that blow is pulled along by gravity, rotating right alongside the solid ground. We are safely cocooned inside this spinning bubble. There is no headwind from the Earth's spin because the air is moving right along with us, just like the calm, quiet air inside the cabin of that airplane. So as you lie there right now, feeling completely stationary, firmly supported by your bed, you are actually a passenger on a gentle, rotating ship. You are gliding smoothly through space, wrapped in a protective blanket of air, looking out the window at a stationary universe that only appears to be wheeling overhead. The stillness you feel in your room is real, but it is the stillness of perfectly balanced, continuous motion. The next time you watch a sunset, try to shift your perspective just a little bit. Instead of watching the sun sink down below the horizon, try to imagine that the sun is completely still and the horizon of the Earth is slowly rolling up to cover it. It is a subtle, beautiful shift in how we see the world, recognizing that we are the ones in motion, dancing quietly in the dark. So what does this actually mean for how our closest neighbor interacts with us? That's what we'll gently explore next. Let's picture the sky once more, not as an endless dome of scattered stars this time, but focusing your attention entirely on the brightest, most familiar object in the night. Picture a silver glowing sphere hanging perfectly quiet in the dark. This is our moon. It is the only other world in the entire universe that human beings have ever walked upon. It is our constant, silent companion, tracing a slow, steady path around the Earth month after month, year after year, just as it has done for billions of years. In your mind, let's travel away from the ground and move closer to it. Leaving the blue and green vibrancy of Earth behind, imagine crossing the silent, empty void of space until the moon fills your entire view. If you were to stand softly on its surface, the very first thing you would notice is the absolute, unbroken stillness. Our Earth is a planet of relentless change. Winds carve our canyons, rains wash away our soil, and restless oceans constantly reshape our coastlines. But the moon has no atmosphere. There is no air, no breeze, no weather of any kind. It is a quiet, stark world of grey, powdery dust and ancient, jagged craters. Because there is no wind to ever disturb anything, the boot prints left by astronauts over half a century ago are still resting there, perfectly preserved in the fine dust, exactly as they were the moment they were made. They will likely remain there for millions of years, locked in an eternal, silent freeze. Although it looks large when it hangs low and heavy over the horizon, the moon is actually quite small compared to our world, about a quarter the size of Earth. To put that into a perspective you can hold in your hands, if the Earth were the size of a basketball resting in your lap, the moon would be about the size of a tennis ball. And though it feels close enough to touch on a clear night, the physical distance between us is vast. If you could somehow point your car straight up into the sky and drive at highway speeds, without ever stopping for gas or rest, it would take you almost 6 solid months of continuous driving to finally arrive at the moon. It is nearly 250,000 miles away. In fact, that gulf of space is so remarkably wide that you could take every single other planet in our solar system, Mars, Jupiter, Saturn, and all the rest, and line them up side by side, and they would all fit beautifully into the empty space between the Earth and the moon. Yet, across all of that staggering distance, the Earth and the moon are locked in a deep, physical embrace. They are tethered together by an invisible, unbreakable bond. We call this bond gravity. You experience gravity every single moment of your life. It is the familiar force that anchors your body to your mattress right now, giving you a comforting sense of weight and physical presence. Every object that has mass, meaning anything made of physical matter, pulls on everything else around it. The more mass an object has, the stronger its pull. Because the Earth is incredibly massive, its gravitational pull is very strong, keeping our feet firmly planted on the ground and holding the moon in its sweeping, circular orbit so it doesn't drift away into the dark. But gravity is never a one-way street. Just as the Earth pulls on the moon reaches back across the void and pulls on the Earth. It is a much gentler pull, because the moon is smaller, but it is entirely real. You can think of this invisible connection like a incredibly long, thick, elastic cord stretched tightly between the center of the Earth and the center of the moon. As the moon slowly glides along its orbital path, that invisible elastic cord tugs consistently at our planet. The solid part of the Earth, the heavy continents, the deep bedrock, the jagged mountain ranges, is incredibly stiff. When the moon pulls on the rock barely yields. But as we know, the Earth is not entirely solid. Over 70% of our world is covered by a relatively shallow layer of free-flowing liquid, the oceans. And water, unlike rock, is incredibly responsive to being pulled. Imagine the Earth wrapped completely in a smooth, glassy layer of water. As the moon exerts its gentle, invisible pull, the water closest to the moon is drawn slightly upward, bulging out towards space. It is as if the ocean is trying to reach out and touch the moon. Interestingly, on the exact opposite side of the Earth, facing away from the moon, the water is effectively left behind by the solid Earth being pulled forward, forming a second, matching bulge. You can picture this like gently squeezing a soft, water-filled balloon in the middle. As it compresses in the center, it stretches outward at both ends. Now, let's connect this directly to the gentle spinning motion we explored a moment ago. We established that the Earth is steadily rotating, like a smooth, silent passenger train. The oceans are resting on the surface of this spinning world, but those two great bulges of water are locked in place, held securely by the moon's invisible tether. As the Earth turns, the solid continents act like massive ships rotating straight into these stationary mounds of water. Imagine sitting quietly on a dark beach. For hours, the wet sand stretches far out in front of you, but as the planet slowly carries your beach directly into one of these oceanic bulges, the water level naturally rises. The waves begin to break further and further up the shoreline. This is what we call high tide. 6 hours later, as the Earth's rotation carries you completely past the bulge and into the thinner, shallower waters between them, the ocean recedes, leaving the wet sand exposed once more. This is low tide. The rhythmic rise and fall of the ocean, relentlessly washing our shores twice every day, is not driven by wind or local weather. It is the deep, physical breathing of the planet in direct response to the gravity of our nearest neighbor. It is a daily, profound reminder, much like the gentle, reassuring tug you might feel when holding hands with a partner while walking through a crowded room. Even when you aren't looking at them, you can feel their presence guiding you, keeping you connected and grounded. This relationship goes even deeper than the oceans. The gravity between our worlds has shaped the moon's actual behavior over billions of years. When the moon was very young, it used to spin much faster on its axis. But the Earth's massive gravitational pull constantly dragged at the moon's uneven shape, creating friction, acting like a very soft, planetary brake. Over unimaginable stretches of time, this braking effect slowed the moon's rotation until it perfectly matched the speed of its orbit around the Earth. Because of this, the moon turns exactly once on its axis every single time it circles our planet. The result of this perfect synchronization is something deeply poetic. The moon always shows us the exact same face. We only ever see one side of it from the ground. The far side of the moon is permanently turned away from us, hidden in eternal mystery. It is as if the moon is a graceful dancer, circling its partner, locked in an unwavering gaze, never once turning its back. The next time you happen to see the moon hanging pale in the daytime sky, or catch its bright reflection on a quiet night, you can look at it with a new sense of intimacy. It is not just a distant, glowing rock. It is the partner that stirs our deep oceans. It is the silent companion that steadies the tilt of our world, making our climate stable enough for life to flourish. It holds us just as we hold it. Let's set that idea down now, fully formed, and let our attention drift toward the brilliant center of our local neighborhood. At the heart of our solar system sits the Sun, a sphere of incandescent gas so unimaginably large that it almost defies our ability to comprehend it. When we stand on Earth, we feel like our planet is the foundation of reality, vast and endless. Our mountains seem impossibly high, our oceans hopelessly wide. But in the grand, sweeping architecture of our solar system, Earth is merely a speck. If you were to hollow out the Sun and pour Earths inside it, you would need over 1 million Earths just to fill the empty space. You can picture the scale like a single, quiet grain of sand resting on the floor beside a massive, brightly glowing exercise ball. The Sun is the undisputed anchor of our neighborhood. It contains over 99% of all the mass in the entire solar system. Everything else, all the planets, the moons, the endless asteroid belts, the comets wandering in the dark, is just leftover debris, the tiny fraction of a percent of material that didn't get swept up into the center when the solar system was formed. When we look up at the Sun in the daytime sky, or feel its intense heat on our faces during the height of summer, it is incredibly natural to think of it as a giant, roaring fire. It glows brightly, it gives off a tremendous amount of heat, and it looks very much like a colossal bonfire suspended in the sky. But the Sun is not on fire at all. For a fire to burn, whether it is a candle on your dining table or a campfire in the woods, it requires oxygen to consume. Space is a complete vacuum. There is no air, no oxygen, and no fuel to burn in the traditional sense. The sun operates on a mechanism that is entirely different and far more profound than simple combustion. It is not made of solid ground, nor is it a liquid ocean. It is composed entirely of plasma, a swirling, electrically charged soup of gas, primarily hydrogen and helium, stretching almost 1,000,000 miles across. To understand how this massive sphere actually works, we need to travel inward in our minds, sinking down through its brightly glowing outer layers, plunging deep into the very center of the star. As you descend, the weight of all that gas above you begins to press down. Because the sun is so incredibly massive, its gravitational pull is fiercely intense. Gravity is constantly trying to crush the sun inward on itself, squeezing all of that surrounding gas tightly toward the exact center. By the time you reach the sun's core, the pressure is so extreme that it is almost impossible to describe using earthly terms. It is the equivalent of having the weight of an entire mountain resting entirely on the head of a single pin. Alongside this unimaginable pressure, the temperature rises to tens of millions of degrees. In this incredibly hostile, densely packed environment, the normal rules of how atoms behave begin to break down entirely. Imagine the deepest part of the sun's core as an incredibly crowded, wildly energetic room. The space is packed, shoulder to shoulder, with hydrogen atoms, moving at blistering speeds. Normally, these atoms would naturally repel one another, much like trying to force the matching poles of two strong magnets together. They instinctively want to push apart. But the crushing pressure of gravity and the extreme heat are so relentless that the atoms have absolutely no choice. They are violently slammed into each other with such overwhelming force that their natural defenses fail, and they actually fuse together. When these hydrogen atoms merge, they create a new, slightly heavier element called helium. This ongoing process is called nuclear fusion. It is the fundamental engine of the stars. But here is the truly beautiful part of this quiet, violent interaction. When those hydrogen atoms fuse into helium, the new helium atom actually weighs slightly less than the pieces that created it. A tiny, microscopic fraction of the physical mass is lost in the collision. That missing mass does not simply vanish from the universe. Instead, it is transformed directly into pure, radiant energy. This transformation follows the most famous relationship in all of physics, the principle that energy equals mass times the speed of light squared. You do not need to calculate anything to understand this. Conceptually, it simply means that trapped inside every piece of physical matter is a towering, sleeping giant of energy. The speed of light is a staggeringly huge number, and when you multiply it by itself, it becomes almost impossibly large. So, even the tiniest speck of physical mass, when converted completely, releases a monumental, city-powering amount of energy. Every single second, deep in the silent, crushing core of the sun, millions of tons of matter are erased from physical existence, translated instantly into blinding light and searing heat. This continuous, silent explosion pushes outward against the crushing weight of gravity. It is the ultimate balancing act in nature. Gravity relentlessly tries to collapse the star inward, while the endless nuclear fusion pushes outward. For billions of years, these two colossal forces have remained perfectly matched, creating the stable, glowing sphere we rely on every day. But the energy created in that core does not have an easy journey to the outside. Once a particle of light, called a photon, is born in the center of the sun, it tries to speed away toward the surface. However, the plasma inside the sun is so incredibly thick and dense that the light particle immediately crashes into another atom, bouncing off in a random direction. It is like trying to sprint blindly through a dense, confusing maze where the walls are constantly shifting. The particle of light zigs and zags, bouncing billions of times, slowly working its way outward. It can take tens of thousands, sometimes hundreds of thousands of years for a single particle of light to finally navigate its way out of the dense interior and reach the outer edge of the sun. Once it finally breaks free from the surface, however, its journey changes completely. Suddenly, there is nothing in its way. The light races across the silent, empty vacuum of space at its maximum speed. It crosses the 93 million miles of dark, freezing emptiness between the sun and the Earth in just about 8 minutes. Think about that the next time you step outside on a quiet morning. When you close your eyes and turn your face upward, you feel a gentle, comforting warmth spreading across your cheeks. The energy you are feeling at that exact moment is ancient. It was forged in the unimaginably violent, crushing core of a star long before human history even began. It spent 100 millennia fighting its way through a blinding maze to reach the surface, and then flew silently across the vast gulf of space for 8 uninterrupted minutes, all just to finally land softly on your skin. It connects you directly, physically, to the very heart of our local star. A moment ago, we ended with the idea of the sun radiating heat outward. Let's pick up that thread right where we left it and see what that warmth touches first. Orbiting closest to the brilliant fire of the sun are 4 relatively small solid worlds. You can think of them as the downtown real estate of our solar system. Just as the center of a bustling city is densely packed with heavy concrete, steel, and stone, the inner solar system is packed with heavy, dense materials. To understand why this is, you have to imagine the very early days of our solar system, billions of years ago. When the sun first ignited, it sent out a powerful, sweeping wind of energy. This solar wind was so intense that it literally blew all the lighter, wispy gases like hydrogen and helium far out into the deep, freezing suburbs of space. All that was left behind in the glaring heat were the heavy, stubborn materials that simply refused to be blown away: iron, nickel, silicon, and rock. Over time, gravity pulled this heavy debris together to form the 4 rocky planets. These are worlds with hard ground. They are places where, if you were wearing the right protective suit, you could plant your boots directly onto the surface and look up at the sky. The very first of these worlds, sitting closest to the sun, is Mercury. If you were to picture Mercury in your mind, it looks remarkably similar to our own quiet moon. It is a small, silent sphere, colored in pale grays and dusty charcoals, and its surface is heavily scarred with thousands of ancient craters. Because Mercury is so close to the sun, it is locked in a brutal environment. However, the most fascinating thing about Mercury is its extreme contrast. Mercury has virtually no atmosphere. It has no blanket of air to hold onto the warmth it receives. Because of this, the side of the planet facing the sun is baked to an unimaginably fierce heat, hundreds of degrees above boiling. But on the exact opposite side of the little planet, cloaked in the shadows of the long, dark night, the temperature plunges into the bitter, freezing cold of deep space. You can imagine the feeling of standing too close to a roaring, towering bonfire on a freezing winter night. The side of you facing the flames feels like it is burning, while your back is shivering in the icy air. Mercury lives its entire existence in that exact, stark division. Moving one step further outward from the sun, we arrive at the second planet, Venus. For a long time, Venus was called Earth's sister planet because it is almost exactly the same size and made of the same heavy rock. But Venus is a cautionary tale of how terribly wrong things can go in the delicate balance of a planet's climate. If you were to fly toward Venus, you would never see its solid surface. The entire planet is permanently wrapped in incredibly thick, swirling, creamy yellow clouds. These clouds are not made of gentle water vapor like ours. They are laced with toxic acids. And beneath those clouds lies an atmosphere composed almost entirely of carbon dioxide. You likely already know how a greenhouse works on Earth. The glass walls let the sunlight in, but they stop the heat from escaping, keeping the plants inside warm even on a cold day. You experience this same effect when you leave your car parked in the glaring summer sun with the windows rolled up tight. The sunlight passes through the windshield, heats up the dashboard and the seats, and that heat is trapped inside the cabin. Venus is the ultimate runaway version of this exact process. Its thick atmosphere lets the sun's intense energy in, but absolutely refuses to let it back out. Because of this trapped heat, the surface of Venus is actually hotter than Mercury, even though it is further away from the sun. The ground is hot enough to melt lead. Adding to this extreme environment is the sheer weight of the air. The atmosphere is so incredibly thick and heavy that standing on the surface of Venus would feel like being crushed under thousands of feet of deep ocean water. It is a stifling, intensely pressurized oven of a world, hidden entirely beneath a pale, beautiful veil of clouds. Next, we take another step outward, and we find a rare, vibrant oasis suspended in the dark. We find Earth. Our home rests in a very specific, narrow band of space surrounding the sun, a region scientists often refer to as the Goldilocks zone. We are not so close to the sun that our oceans boil away into steam, as they would on Venus or Mercury, and we are not so far away that our oceans freeze solid into global ice. We sit at the precise, perfect distance where water can exist as a free-flowing liquid, pooling in deep basins, carving winding river valleys, and falling gently from the sky as rain. Water is the great solvent, the vital ingredient that allows chemistry to become biology. It is because of this perfect, quiet balance of temperature and atmospheric pressure that you are able to lie in your bed tonight, breathing cool, oxygen-rich air, safely sheltered from the freezing vacuum of space. Earth is a magnificent, fragile blue and white marble, a testament to the beautiful coincidences of nature. Finally, we cross one more gap of space to reach the fourth and final rocky world, Mars. If Earth is a vibrant oasis of liquid water, Mars is a quiet, frozen desert. Picture a world covered entirely in fine, reddish-orange dust. This color comes from the exact same chemical process that causes an old bicycle chain to rust when left out in the rain, iron oxidizing. Mars is literally a rusted planet. It is much smaller than Earth, with a very thin, wispy atmosphere that does almost nothing to trap the sun's fading heat. Because of this, it is bitterly cold. If you were to stand on the rusty soil of Mars and look around, the landscape would look surprisingly familiar, like the arid deserts of the American Southwest, but stretched to an immense, planetary scale. You would see sprawling dune fields, scattered boulders, and rolling hills. Mars is home to physical features that dwarf anything on Earth. It holds a staggering canyon system that is incredibly deep, and so wide that it would stretch all the way from the east coast of the United States to the west coast. It is also home to ancient, extinct volcanoes that rise 3 times higher than Mount Everest, sloping gently up into the thin, pinkish sky. Today, Mars is entirely silent. Its volcanoes no longer erupt, its rivers dried up billions of years ago, and only the faint, cold wind still moves the rust-colored dust across the plains. It is a world frozen in time, quietly holding the secrets of its warmer, wetter past. These 4 worlds, baked Mercury, suffocating Venus, vibrant Earth, and frozen Mars, make up our quiet inner neighborhood. They share a deep family resemblance, born from the same heavy rock and metal, all huddled together in the warmth of the sun's glow. Before we rest here, let me whisper where we're headed next, not to rush, but to plant a seed about the borders that separate these quiet neighborhoods. As we leave the rusted, frozen deserts of Mars behind us in our imagination, the environment of our solar system begins to subtly but unmistakably change. The brilliant warmth of the sun is fading, growing slightly dimmer and slightly more distant with every million miles we travel outward. We are entering a vast, wide gulf of space that sits like a grand, quiet frontier. This expansive borderland separates the small, dense, rocky planets we have just visited from the massive, swirling giants that lie ahead in the dark. This wide expanse is known as the asteroid belt. When you hear the words asteroid belt, you might instantly picture a thrilling scene from a science fiction movie. It is incredibly common to imagine a dense, chaotic minefield of massive, tumbling boulders violently crashing into one another, sending sparks and debris flying into the void. You might picture a scenario where a spacecraft must frantically dodge, weave, and barrel roll just to survive the journey across. It is a dramatic and exciting image, but the reality of space is far more serene, and in its own quiet way, far more beautiful. The truth is that space is overwhelmingly, unimaginably vast. The distances involved are so large that our earthly intuition completely fails us. If you were to gather up every single asteroid in the entire belt, millions upon millions of pieces of rock and metal, and mash them all together into one single solid sphere, that new world would still be significantly smaller than our own moon. Now, take that relatively small amount of material and scatter it across a ring of empty space that is hundreds of millions of miles wide and hundreds of millions of miles thick. Because of this incredible dispersion, the asteroid belt is not a crowded, dangerous highway at all. Instead, it is much more like driving through a sprawling, completely empty desert in the dead of the night, on a road so isolated that the next car might be 100 miles away. If you were somehow able to stand on the surface of a typical asteroid in this belt, and you looked up into the dark, freezing sky hoping to wave at your neighboring rocks, you likely would not see anything at all. The nearest asteroid would be millions of miles away from you. It might appear only as a faint, distant speck of light, completely indistinguishable from the background stars. Our spacecraft from Earth have flown through the asteroid belt many times on their way to the outer planets, and they do not have to steer around anything. They simply sail straight through the dark, completely undisturbed, because the emptiness is so absolute. So, what exactly are these solitary wanderers? You can think of asteroids as the leftover building materials of our solar system. Imagine a large construction site where a beautiful, complex house has just been finished. The workers have packed up their tools, the heavy machinery is gone, the new owners have moved in, and the neighborhood is quiet. But if you walk around to the far edges of the property, hidden in the tall grass, you might find a scattered pile of spare bricks, a few stray pieces of lumber, and a handful of unused nails. The asteroids are just like those forgotten scraps. They are the ancient fragments of rock, heavy iron, and ice that never quite managed to pull themselves together to become a finished, polished planet. They are pristine, untouched relics from the very dawn of our solar system, suspended in the dark for over 4 billion years. You might naturally wonder why they never came together. Why didn't gravity do what gravity always does, and gently pull all these fragments into a single, new rocky world to fill the gap between Mars and the outer giants? The answer lies just beyond the belt itself, resting in the immense, looming presence of the planet Jupiter. Jupiter is so staggeringly massive that its gravitational pull reaches far across the solar system, acting like an invisible, disruptive wave. Imagine you are trying to sweep a large pile of scattered dust into a neat, single mound on your kitchen floor, but someone is constantly, rhythmically shaking the floorboards underneath you. Every time the dust begins to gather together into a pile, the shaking scatters it apart again. For billions of years, Jupiter's massive gravity has been shaking the floorboards of the asteroid belt. Every time these rocks drifted close enough to perhaps join together under their own weak gravity, Jupiter's massive gravitational presence would sweep past as it orbited the Sun, stirring them up, increasing their speeds, and causing them to gently bump and shatter apart rather than quietly merging. And so, they remained forever separated, a fractured planetary dream suspended in time. Because they never had enough mass to create the strong, inward, crushing gravity required to pull themselves into perfect, smooth spheres. Most asteroids are wildly irregular in shape. They look like jagged, uneven potatoes or elongated blocks of rough, pitted stone. Some are solid chunks of incredibly dense iron and nickel, heavy and unyielding. Others are entirely different. They are essentially giant, floating piles of rubble, barely held together by their own incredibly weak gravity. If you were to gently jump on one of these rubble pile asteroids, the gravity would be so faint that your legs might push you completely off the surface, sending you drifting slowly and silently away into the void. But there is one magnificent exception resting quietly in this scattered field. Floating in the middle of the asteroid belt is a world named Ceres. Ceres is the undisputed queen of the belt. It is so large that it contains nearly a third of all the mass in the entire region. Because it is so massive, its gravity finally won the battle against the rock, pulling its material into a beautifully smooth, round sphere. Ceres is considered a dwarf planet. It is a quiet, icy world, draped in darkness, with mysterious bright spots of salt glowing faintly on its surface, hinting at the possibility of ancient, frozen oceans hidden deep beneath its crust. It drifts through the sparse, empty darkness of the belt like a solitary, dignified ship navigating a vast, quiet sea. The asteroid belt, then, is not a place of chaos, noise, or danger. It is a peaceful, silent archive. It is a grand museum of planetary history, where the raw, unshaped ingredients of the universe have been quietly preserved in the deep freeze of space, completely untouched for billions of years. They just drift, slowly tumbling in the fading light of the distant sun, keeping the ancient secrets of how our world, and all the rocky worlds around us, first began. And with that understanding quietly in place, we're naturally led to ask what massive structures exist beyond this rocky divide. As we drift beyond that rocky divide, crossing the vast and quiet expanse of the asteroid belt, the very nature of the solar system shifts dramatically. We are now traveling far from the comforting warmth of the sun. If you were to look back toward the center of our solar system from this vantage point, the sun would no longer look like the large, warming fire that graces our earthly skies. It would appear simply as a brilliantly bright star, a piercing point of light in the deep black, too distant to offer any real heat. Out here in the cold, the small, heavy worlds of rock and iron give way to something entirely different. We have entered the realm of the giants. The first of these colossal worlds is Jupiter. To simply call Jupiter a planet almost feels like an understatement. It is a world of staggering, overwhelming scale. It is so massive that it weighs more than twice as much as all the other planets, moons, and asteroids in the solar system combined. If Earth were the size of a small coin resting in your palm, Jupiter would be the size of a large dining table. But unlike Earth, Jupiter has no solid ground. It is composed almost entirely of hydrogen and helium, the exact same light, wispy gases that make up the Sun. If you were to slowly descend toward Jupiter, you would never find a surface to land on. You would sink into its upper atmosphere, surrounded by towering, swirling clouds of ammonia. As you drifted deeper, the gas would gradually grow thicker and heavier around you. The pressure would steadily build, and the atmosphere would slowly, seamlessly transition from a thick fog into a dense fluid. Deep inside the planet, the pressure becomes so immense that the hydrogen gas is crushed into a bizarre, swirling liquid metal. Jupiter is essentially a boundless, bottomless ocean of heavy fluid and gas, churning in the dark. From the outside, however, Jupiter is a masterpiece of turbulent motion. Because the planet spins incredibly fast, completing a full day in just about 10 hours, its outer atmosphere is whipped into horizontal bands of high-speed winds. When you picture Jupiter, Imagine these beautiful parallel stripes wrapping completely around the sphere, painted in rich shades of cream, burnt orange, pale yellow, and rust red. They look very much like the marbled patterns you see when you slowly stir heavy cream into a dark cup of coffee. Swirling within these bands are massive storms, the most famous being the Great Red Spot. This is a swirling, high-pressure hurricane that has been churning continuously for hundreds of years. It is a storm so impossibly large that you could drop our entire Earth directly into the center of it, and it would easily be swallowed up by the crimson winds. Moving further outward, into the dark, we arrive at the second giant, Saturn. Saturn is slightly smaller than Jupiter, glowing with a soft, muted golden hue. Despite its massive size, Saturn is surprisingly light. It is the least dense planet in our entire solar system. To put it into an earthly perspective, if you could somehow find an ocean of water large enough to hold it, Saturn would not sink to the bottom. It would bob gently on the surface, much like a cork or a wooden apple floating in a barrel. But Saturn is most famous for what surrounds it. Wrapping around the equator of this golden sphere is the most breathtaking structure in our neighborhood, the ring system. In older photographs, these rings look like a few solid, flat disks of plastic, but they are not solid at all. Saturn's rings are composed of billions upon billions of individual pieces of water, ice, and rock. Some pieces are as small as grains of sand or flakes of snow, while others are the size of boulders, or even as large as a small house. Every single one of these icy fragments is caught in Saturn's gravitational pull, orbiting the planet in a perfectly choreographed, silent ballet. Because they are made largely of ice, they catch the faint, distant light of the sun and reflect it brilliantly into the dark. What is most astonishing about the rings is their proportions. They are incredibly wide, stretching out for tens of thousands of miles, yet they are unimaginably thin. If you were to scale Saturn down to the size of a basketball, the rings spreading out from it would be thinner than a single sheet of tissue paper. They are a fragile, delicate halo of crushed ice, spinning eternally around a gas giant. As we journey even further away, the temperature plummets again. We leave the gas giants behind and enter the domain of the ice giants, Uranus and Neptune. They are smaller than Jupiter and Saturn, though still large enough to hold dozens of Earths inside them. They are called ice giants because, beneath their thick atmospheres of hydrogen and helium, their deep interiors are filled with a heavy, slushy mix of water, ammonia, and methane, compressed to extreme pressures. First is Uranus, a serene pale sphere the color of a robin's egg or a light, icy cyan. That beautiful blue-green color comes from methane in its upper atmosphere, which absorbs the red light from the sun and reflects only the cool blue back out into space. Uranus holds a very strange secret. While Earth and the other planets spin like upright tops as they travel around the sun, Uranus is tilted completely on its side. It doesn't spin. It rolls along its orbital path, much like a heavy barrel rolling across a dark floor. This means that for decades at a time, one entire half of the planet is bathed in faint, continuous daylight, while the other half is plunged into a bitterly cold, decades-long night. Finally, we reach the furthest planet from the Sun, Neptune. It is a twin to Uranus in size and composition, but its color is a deeper, richer cobalt blue. It looks like a heavy sphere of deep ocean water suspended in the blackness. Neptune is an incredibly violent world, home to the fastest, most relentless winds in the solar system, whipping through its freezing atmosphere at supersonic speeds. It is so unimaginably far from the Sun that it takes Neptune over 160 Earth years just to complete a single, slow orbit. From the cloud tops of Neptune, the Sun is nothing more than a bright, lonely pinprick in the eternal night. These four massive worlds, the swirling storms of Jupiter, the icy halo of Saturn, the tilted silence of Uranus, and the deep blue storms of Neptune stand as colossal sentinels in the outer dark. They have no solid ground, no warm shores, just endless crushing depths of gas, fluid, and ice. So what does this actually mean for where our solar system ends? That's what we'll gently explore next. As we leave the deep, stormy blue of Neptune behind, we enter a region of space where our earthly intuition about borders and boundaries begins to blur. On Earth, we are entirely used to clear, distinct lines. A winding river separates two towns. A wooden fence marks the edge of a quiet backyard. A sandy coastline definitively divides the solid land from the rolling sea. We expect endings to be sharp and noticeable. But in the quiet, sweeping architecture of the cosmos, borders are rarely drawn with sharp lines. Instead, they are slow, fading transitions, like the gentle, almost imperceptible shift from twilight into deep night. Past Neptune, the sunlight becomes incredibly faint. If you were to pause and look back toward the center of our solar system from this immense distance, the sun would no longer cast a warm, comforting glow. It would simply look like a very bright, piercing star, appearing no larger or brighter than a thin crescent moon on a clear winter night. It offers absolutely no heat. The temperature out here plunges to hundreds of degrees below zero. We are quietly stepping out of the brightly lit, bustling neighborhoods of the planets and venturing far out into the vast, freezing, unlit suburbs of our local system. This sprawling, dimly lit region just beyond Neptune is known as the Kuiper Belt. You can think of it as a much larger, significantly colder cousin to the asteroid belt we traveled through earlier. But whereas the asteroid belt between Mars and Jupiter is forged almost entirely from heavy rock and iron, the Kuiper Belt is built from ice, and it is not just frozen water. Out here in the deep freeze of the outer solar system, gases that we normally breathe or use as fuel on Earth like methane, ammonia, and nitrogen are chilled so completely that they freeze into solid, rock-hard ice. The Kuiper Belt is a staggeringly wide ring made of this frozen debris, slowly circling the distant sun in the dark. It is vast beyond earthly comprehension. If you could somehow drive a car across its width at highway speeds, it would take you centuries of continuous travel just to reach the other side. Yet, just like the asteroid belt, it is overwhelmingly empty. The icy bodies that live here are scattered so widely, separated by millions of miles of empty black vacuum, that they almost never interact. They are solitary drifters. They are the pristine, ancient, untouched remnants from the very earliest days of our solar system's creation, preserved perfectly in this ultimate deep freeze. For a very long time, humanity thought of this dark region simply as the home of the ninth planet, Pluto. But as our technology improved, and our vision sharpened to peer deeper into the dark, we realized a beautiful truth. Pluto was never alone. It is, in fact, one of the largest and most prominent members of a thriving, silent community of icy worlds drifting within the Kuiper Belt. Picture Pluto not as a planetary outcast, but as a king of this frozen frontier. It is a quiet, stunningly beautiful world. Thanks to the robotic messengers we have sent across the dark ocean of space, we now know that Pluto is not just a dead, featureless rock. It holds towering, jagged mountains made entirely of solid water ice, rising as high as the Rocky Mountains on Earth, pushing up into a thin, hazy blue atmosphere. It even possesses a massive, brilliant, heart-shaped glacier resting peacefully on its surface. This vast plain is made of frozen nitrogen that slowly flows, churns, and shifts, much like slow-moving glaciers do on Earth, despite the unimaginably bitter cold. Pluto's orbit is so incredibly wide and slow that it takes nearly 250 Earth years to complete a single journey around the Sun. Since the day it was first discovered by human eyes, it has not yet completed even half of a single lap. As we move even further out, past Pluto and the scattered icy bodies of the Kuiper Belt, we reach a different kind of invisible border. Throughout our journey from the center, we have focused entirely on the sun's gravity, but the sun also breathes. It constantly exhales a rushing wind of charged particles, blowing outward in every direction, creating a massive, protective magnetic bubble around all the planets. This immense bubble is called the heliosphere. It shields us from the harsher radiation of the wider galaxy. But eventually, pushing against the endless void, that solar wind runs out of momentum. It presses against the thin, quiet gas that drifts in the spaces between the stars, and finally, it yields and comes to a complete stop. This invisible boundary, where the sun's breath finally gives way to the pressure of the interstellar wind, is considered by many to be the true edge of interstellar space. If you were to cross this quiet threshold, you would leave the protective atmosphere of our local star behind, stepping fully into the uncharted waters of the cosmic ocean. But remarkably, even here, in this profound and distant darkness, the sun's gravity has not entirely let go. To find the true, absolute edge of our solar system's gravitational reach, we must travel out to distances that truly boggle the human mind. Far, far beyond the icy plains of the Kuiper Belt, far beyond the protective reach of the solar wind, lies an unimaginably vast structure known as the Oort cloud. Unlike the flat, disk-like rings of the planets and the asteroid belts we have seen so far, the Oort cloud is a colossal, spherical shell. Imagine a gigantic, hollow, invisible bubble enclosing absolutely everything we have explored up to this point. This shell is so incredibly distant that light itself, moving at the fastest speed possible in the universe, takes months or even years just to cross the distance from the sun to this outer edge. The Oort cloud is a deeply frigid, invisible reservoir populated by trillions of dormant comets. You can think of these comets essentially as dirty snowballs, chunks of pristine ice, rock, and ancient dust, hanging suspended in the absolute blackness. They are barely held by the sun's fading gravitational grip. Out here, the sun's pull is no longer a commanding force. It is merely a gentle, whispered suggestion, a fragile, almost imperceptible tether. For millions upon millions of years, these icy fragments do nothing but drift in the absolute dark, slowly and silently orbiting in total isolation. But very occasionally, this delicate, ancient balance is disturbed. As our entire solar system sweeps through the Milky Way galaxy, the gravity of a completely different, passing star might reach out and give one of these dormant snowballs the tiniest, gentlest gravitational nudge. That subtle shift is just enough to break the fragile tether. The icy body will slowly begin a millions of years-long fall inward, dropping out of the quiet Oort cloud and diving down toward the warmth of the inner solar system. As it finally gets closer to the sun, the ancient ice begins to heat up and vaporize, trailing a brilliant, glowing tail of gas and dust across the sky. This is exactly what we see when a spectacular comet visits our night sky on Earth, a frozen, silent traveler from the very outermost edge of our solar system, making a brief, beautiful, glowing appearance in our neighborhood before rushing back out into the dark. The Oort cloud is the final, quiet frontier. It is the outer, invisible wall of our cosmic home, holding the memories of our solar system's birth in a state of perfect, frozen slumber. Let's set that idea down now, fully formed, and let our attention drift toward the spaces between the stars. When we stand on the edge of the Oort cloud in our imagination and look outward into the deep cosmic ocean, the distances become so unimaginably vast that the ways we normally measure things on Earth simply break down. On our planet, we use very human scales, built entirely for human experiences. We measure our lives in inches, feet, miles, or kilometers. These units make perfect sense for measuring the length of a hallway, the distance from your house to the grocery store, or the long stretch of a cross-country road trip. But once you leave our solar system and venture out into the interstellar void, trying to measure the dark with miles is like trying to measure the distance between two continents using a single blade of grass. The numbers become so incredibly large, padded with so many meaningless zeros, that the human brain simply cannot hold on to them. They lose all their weight and significance. We need a new way to measure the void, something built not for earthly roads, but for the universe itself. To measure the cosmos, we rely on the single fastest thing in existence, light. Think about turning on a lamp in a dark, quiet room. The very instant your finger presses the switch, the room is flooded with illumination. To our human eyes, light seems instantaneous. It doesn't appear to travel, it just simply exists the moment it is summoned. But light is actually moving. It is physically traveling through the space in your room, flying from the glowing bulb to the walls, bouncing off the pages of a book, and finally entering your eyes. It just moves so remarkably fast that our brains cannot perceive the journey. In the absolute vacuum of space, where there is no air, no dust, and no friction of any kind to slow it down, light travels at a constant, blistering, ultimate speed limit. It moves at 186,000 miles every single second. Imagine snapping your fingers. In the brief moment it took to make that sound, a beam of light could travel entirely around the Earth's equator more than 7 times. It is a speed so fast it almost feels like magic, but it is the fundamental speed limit of our reality. If you were to let a beam of light travel completely uninterrupted at that staggering speed for one entire Earth year, it would cover nearly 6 trillion miles. That unfathomable distance, the stretch of space that light can traverse in one 12-month period, is what we call a light year. It is deeply important to remember that a light year, despite having the word year right there in its name, is a measure of physical distance, not a measure of time. It is exactly like how you might describe a weekend getaway. If someone asks how far away a cabin is, you might say, it is a 3-hour drive. The 3 hours isn't time itself. It's a convenient, relatable way of describing the long stretch of highway between your home and your destination. When astronomers say a star is 4 light years away, they mean it is resting at a distance of about 24 trillion miles. We use light years as the standard yardstick of the cosmos because it gathers up all those overwhelming zeros and packages them into numbers that are small, elegant, and easy for our minds to grasp. But using the speed of light to measure the universe gives us something far more profound than just a convenient ruler. It quietly gives us a time machine. Because light takes time to travel from one place to another, whenever you look out into space, you are never, ever seeing the universe as it is right exactly now. You are always looking backward in time. Think of it like receiving a handwritten letter in the mail from a dear friend who lives across the ocean. If it takes a week for the heavy envelope to cross the water and reach your mailbox, the news you are reading inside is already a week old. You are experiencing your friend's thoughts, feelings, and updates exactly as they were 7 days ago, not as they are in the present moment. Space works in the exact same way, just on a much grander, silent scale. Even the warm sunlight resting on your face on a quiet afternoon is essentially a letter in the mail. It takes light about 8 minutes to cross the 93 million miles of space between the Sun and the Earth. If the Sun were to suddenly, miraculously blink completely out of existence, we would not know it right away. The sky would remain bright, the air would remain warm, and the shadows on the ground would remain sharp for 8 full minutes, because the last of the Sun's light would still be in transit, traveling silently across the void toward us. We are always experiencing our Sun exactly as it was 8 minutes in the past. Now, take that beautiful concept and apply it to the quiet, dark field we imagined at the very beginning of our journey. When you lie on your back and look up at the glittering night sky, the stars you see are resting at vastly different distances from Earth. The closest star system to our Sun is just over 4 light-years away. When you look at its faint light, you are seeing that star exactly as it was 4 years ago. You are looking at a 4-year-old ghost. Other stars you can easily see with your naked eye are tens, hundreds, or even thousands of light-years away. When you gaze at a bright star that is 1,000 light-years distant, the light striking your eye tonight left that star 1,000 years ago. It began its journey long before the modern world existed, long before most of our modern cities were ever built. That tiny beam of light traveled through the silent, freezing dark for 10 straight centuries, perfectly undisturbed, crossing trillions upon trillions of miles of empty space, just to end its unimaginably long journey by landing softly on the surface of your eye. And when we use powerful orbital telescopes to peer even deeper into the black, into the realms of other distant galaxies, we are looking millions, sometimes billions of years into the past. We can see galaxies exactly as they were when the universe itself was still young, glowing with the fierce, turbulent light of newborn stars. What this ultimately means is that the night sky is not a single, flat portrait of the present moment. It is a deeply layered, living archive of cosmic history. Every time you tilt your head back to look at the stars, you are not just looking across space, you are looking deep into time. You are seeing different eras of the universe's history, all layered on top of one another in a single, quiet glance. It is a profoundly humbling and comforting realization. It reminds us that we are intimately connected to a deep, sweeping timeline that stretches far beyond our own lives, and that the universe has been carrying on its quiet, majestic dance for eons before we arrived. A moment ago, we ended with the idea of starlight traveling through the dark. Let's pick up that thread right where we left it and look at where those stars actually come from. When we lie on the ground and look up at the night sky, the stars feel like the very definition of permanence. We build our calendars and navigate our ships by them because they seem to never, ever change. If you were to look at a star map drawn by an ancient astronomer thousands of years ago, the sky would look virtually identical to the one resting above you tonight. Because human lives are so brief, it is entirely natural for us to assume that the stars have simply always been there and that they always will be. But this feeling of eternal stillness is an illusion. The universe is deeply alive. Stars are not permanent fixtures bolted to the ceiling of the dark. They are born. They live out their long, sweeping lives, and eventually, they die. To understand how something as massive and brilliant as a star can actually be born, we have to imagine a place that is the exact opposite of a star. We have to picture a place that is overwhelmingly dark, unfathomably cold, and incredibly still. These birthplaces are called nebulae. A nebula is a colossal, drifting cloud of gas and dust suspended in the deep, empty spaces between the stars. When you hear the word cloud, it is easy to picture the fluffy, white, water-filled clouds that drift across a summer sky here on Earth. But a nebula is entirely different. It is a sprawling, silent fog composed almost entirely of hydrogen gas, mixed with microscopic grains of carbon and silicon dust. And it is vast beyond all human comprehension. A single stellar nursery can span dozens, sometimes hundreds, of light years across. Inside this cloud, the temperature is unimaginably cold, hovering just slightly above the absolute lowest temperature physically possible in the universe. Because it is so bitterly cold, the gas and dust barely move. There is no wind, no glowing light, no churning storms. The nebula simply rests in the dark, a quiet, sleeping reservoir of raw material, waiting with infinite patience. For millions of years, absolutely nothing happens. But eventually, that profound stillness is broken. A star cannot be born without a gentle push. Imagine you are sitting quietly in your living room, and a large, heavy truck drives past your house on the street outside. Even if you cannot see the truck, you can feel the deep, low rumble of its engine vibrating through the floorboards, and you might hear the windows rattle slightly in their frames. The energy from the truck travels through the ground and the air, disturbing the quiet of your room. In the cosmos, the same thing happens, but on a majestic scale. The spark that wakes the sleeping nebula often comes from far away. It might be the colossal shockwave of a distant, dying star exploding, or it might simply be the gravitational ripples of the entire galaxy slowly turning. Whatever the cause, a massive, silent wave of pressure ripples through the freezing cloud of gas. As this invisible wave passes through the nebula, it pushes the scattered atoms of hydrogen and the tiny grains of dust just a little bit closer together. And in the quiet architecture of the universe, moving things closer together changes everything, because it awakens gravity. We talked earlier about how every object with mass pulls on everything else. When the shockwave pushes a few wisps of gas together, that slightly denser patch of cloud suddenly has a slightly stronger gravitational pull than the empty space around it. It begins to gently tug on the gas nearby. You can picture this process like sweeping a hardwood floor. When you first start sweeping, you are just pushing a few scattered dust bunnies together. But as your pile grows larger, it becomes much easier to sweep more debris into it. The pile becomes a focal point. In the nebula, gravity is the broom. The small, dense patch of gas slowly pulls in more hydrogen. As it gathers more mass, its gravitational pull becomes even stronger, which allows it to pull in material from even further away. It is a slow, quiet, self-feeding cycle. As millions of tons of gas and dust begin to fall inward toward this newly forming center, the material starts to spin. Imagine water slowly spiraling as it glides toward a drain, or a potter working a piece of wet clay on a spinning wheel. The massive cloud flattens out into a wide, rotating disk, with a heavy, dense ball of gas gathering right in the very center. This glowing, gathering sphere in the middle is called a protostar. It is the seed of a newborn sun. At this stage, the protostar is not yet shining with true starlight, but it is getting incredibly hot. To understand why, think about using a hand pump to inflate a bicycle tire. As you forcefully push the handle down, squeezing the air into the tight space of the tire, the metal barrel of the pump actually grows warm in your hands. This happens because you are forcing all those moving air molecules into a much smaller space, causing them to bump and rub against each other with immense friction. The physical act of compression creates heat. Now, scale that up to the size of a solar system. Gravity is relentlessly crushing a cloud of gas that is billions of miles wide down into a single, dense sphere. The friction of all that hydrogen collapsing inward is monumental. The temperature in the very center of the protostar begins to climb from the bitter, freezing cold of deep space to hundreds of degrees, then to thousands, and then to millions. The gravity continues to squeeze. The heat continues to rise. The protostar glows with a dull, heavy red light, wrapped tightly in its dark, spinning cocoon of leftover dust. It is like a massive engine turning over, trying to start. It requires an exact, critical threshold to truly ignite. The pressure in the core must become so severe, and the heat must reach nearly 10 million degrees for the fundamental rules of chemistry to break down. And then, in the deep, crushing center of that spinning sphere, the threshold is crossed. The hydrogen atoms are squeezed together so violently that they fuse. The sleeping giant of nuclear energy we discussed earlier is finally awakened. A spark of pure, blinding energy is released. The moment nuclear fusion begins, a true star is born. The outward blast of this new, towering energy meets the inward, crushing weight of gravity, and the two forces lock into a perfect, stable balance. The sudden, brilliant ignition sends a fierce wind of light and heat rushing outward, blowing away the remaining disk of gas and dust, clearing the dark cocoon. Where there was once only a freezing, silent fog, a brilliant new sun now shines. casting its pristine light across the cosmic ocean for the very first time. Before we rest here, let me whisper where we're headed next. Not to rush, but to plant a seed about how a star spends the long, quiet years of its life. A moment ago, we ended with the idea of a new star clearing away its dark cocoon and shining for the very first time. Let's pick up that thread right where we left it and look at how a star actually spends the long, quiet years of its life. Once the violent, turbulent birth of a star is over, it settles into an incredibly long, peaceful plateau. In astronomy, this vast, stable chapter is known as the main sequence. It is by far the longest phase of a star's existence, making up about 90% of its entire life. Our own sun is right in the very middle of its main sequence right now, carrying on with a steady, unwavering reliability that makes life on Earth possible. To understand what it means for a star to be in this stable phase, we have to look at the monumental tug-of-war happening deep inside it. A star is essentially a delicate, ongoing compromise between two of the most powerful forces in nature. On one side, there is gravity. As we discussed earlier, gravity is relentless. Because a star is so unimaginably massive, its own gravity is constantly pulling all of its gas inward, trying with all its might to crush the star down into a single, tiny, infinitely dense point. Gravity never sleeps, and it never stops pulling. On the exact opposite side of this cosmic struggle is the outward push of nuclear fusion. Deep in the core, millions of tons of hydrogen are being fused into helium every single second, releasing a towering, blinding explosion of energy. This relentless explosion pushes outward against the crushing weight of the gas above it. You can picture this delicate balance by imagining a common, everyday object, a rubber balloon. When you take a deep breath and blow air into a balloon, the air pressure inside pushes outward, stretching the rubber. At the exact same time, the elastic rubber is pulling inward, trying to force the air back out and collapse the balloon. When the balloon is fully inflated and tied off, it sits perfectly still on the table. It is not still because nothing is happening. It is still because the outward push of the trapped air and the inward pull of the rubber are perfectly matched. They have fought each other to a complete standstill. A star works in this exact same way. The inward crush of gravity and the outward blast of nuclear energy are in a state of perfect, harmonious balance. As long as this balance is maintained, the star remains perfectly stable. It does not shrink, and it does not expand. It just sits in the dark vacuum of space, humming with unimaginable power, casting its warm, steady light out into the cold. But this beautiful balance requires fuel. The star is constantly burning through its deep reserves of hydrogen to maintain that outward pressure against gravity. You can think of a star's hydrogen supply much like a massive savings account that you slowly, steadily draw from over the course of a long lifetime. When the star is newly born, that account is incredibly wealthy. It holds an abundance of resources. For billions of years, the star can comfortably pay the heavy, daily cost of fighting off gravity without ever worrying about the balance dropping too low. However, the fuel is finite. The savings account is not bottomless. Slowly, imperceptibly, over billions of quiet years, the hydrogen atoms in the very center of the star are converted into heavier helium. As the helium builds up, it acts almost like a very dense, heavy ash collecting in the bottom of a fireplace. Because helium is heavier than hydrogen, it sinks to the very center of the core, and it is much harder to burn. Eventually, the star reaches a turning point. The readily available hydrogen in the core begins to run desperately low. The outward push of nuclear fusion begins to weaken, just a little bit. And gravity, which has been waiting patiently for billions of years, seizes the opportunity. Because the outward pressure has dropped, gravity begins to win the tug-of-war. The core of the star is violently squeezed and crushed inward. But in the universe, crushing something always creates intense heat. As gravity squeezes the core, the temperature inside the star skyrockets to levels it has never experienced before. This new, fierce wave of heat radiates outward from the collapsing center, and it hits the outer layers of the star's gas. When you heat up a gas, it expands. This new, intense heat from the dying core pushes the outer layers of the star far away from the center. The star begins to swell to a monstrous size. It expands so much that it becomes what we call a red giant. This is the fate that awaits our own sun. But there is absolutely no need to worry. This will not happen for another 5 billion years. It is an event resting so far in the distant future that the Earth itself will likely look entirely different by the time it arrives. But if you could somehow stand safely on the surface of the Earth when our sun finally becomes a red giant, the sky would look breathtaking and terrifying. Because the outer layers of the sun have expanded so far outward, they are now much further away from the blazing heat of the core. As the gas stretches out, it actually cools down, and as it cools, its color changes. The brilliant, blinding yellow-white light we are used to seeing will slowly transition into a deep, smoldering, heavy red, like a glowing coal resting in a dying fire. The sun will no longer be a small, bright coin in the sky. It will have swelled so massively that it will swallow the orbits of Mercury and Venus entirely. In the earthly sky, the red sun will fill almost the entire horizon, a colossal dome of soft, crimson light pressing down on the world. The oceans will have long since boiled away into the atmosphere, and the Earth will be baked bare by the immense heat. This phase is the star's swan song. It is a beautiful, tragic expansion, a desperate attempt to find a new balance as its fundamental fuel finally runs dry. The star has spent billions of years as a steady, reliable companion in the dark, and now it is preparing to let go of its outer layers and face the end of its journey. And with that understanding quietly in place, we're naturally led to ask what happens when the fuel finally, completely runs out. For a medium-sized star, like our own steady sun, the end of the journey is not a sudden, violent catastrophe. It is a slow, graceful transition, a quiet fading into the dark. We left off with the star swollen into a massive red giant, its outer layers stretched incredibly far from the core, glowing with a heavy crimson light. But a star cannot hold this bloated, oversized shape forever. It is a deeply unstable arrangement. Deep inside, the core has been frantically fusing heavier and heavier elements, trying to keep the fires burning, trying to hold off the crushing weight of gravity. But eventually, there is simply nothing left to burn. The grand, billions of years long fire, the central engine that has supported the star for its entire existence, finally sputters and goes cold. When that central fire stops, there is no longer any outward push of energy to hold up the colossal weight of the star. But because the star's outer layers have drifted so incredibly far away from the center during the red giant phase, the gravitational grip holding onto them has become incredibly weak. The core simply cannot hold on to its sprawling atmosphere anymore. Imagine taking a deep, tired breath on a freezing winter day, and then slowly, gently exhaling. You can watch your breath form a pale, warm cloud that slowly drifts away from you, expanding and dissipating into the cold air until it completely disappears. This is exactly how a star like our sun says goodbye. It does not explode, it simply lets go. The star gently exhales its outer layers of gas. This beautiful, slow-motion exhalation happens in rhythmic pulses over thousands of years. The layers of hydrogen and helium quietly detach and drift outward into the vacuum of space, expanding like a massive, delicate soap bubble. As this shell of gas drifts away, it is illuminated from the inside by the exposed core left behind. This creates one of the most breathtaking sights in the entire universe, a glowing, expanding cloud of vibrant, luminous color suspended in the blackness. We call this a planetary nebula. Through a telescope, these drifting clouds look like intricate cosmic flowers or delicate, glowing butterflies, painted in deep neon greens, rich reds, and soft blues. It is a beautiful, silent monument to the star that once was, enriching the empty spaces of the galaxy with the heavy materials it forged during its long life. But as that beautiful, expanding cloud of gas slowly drifts away, eventually fading into the dark over tens of thousands of years, something remains right at the very center of where the star used to be. Stripped of all its outer layers, the heart of the star is finally exposed. We call this remaining core a white dwarf. A white dwarf is a magnificent and deeply strange object. It is no longer a functioning star, because there is no nuclear fusion happening inside it anymore. The fire is entirely out. What you are looking at is essentially the dense, heavy ash left behind by billions of years of burning. But because gravity was the last force to win the tug of war, this core has been crushed down to an almost unimaginable density. Think about the sheer scale of what has happened. The star has taken roughly half the total mass of our original sun, a weight so massive it could hold entire solar systems in orbit, and gravity has ruthlessly squeezed all of it down into a single, hard sphere, no larger than the planet Earth. To try and grasp how densely packed this material is, imagine holding an ordinary teaspoon from your kitchen drawer. If you were to walk outside and scoop up a teaspoon of normal dirt from a garden, it would weigh almost nothing. If you scooped up a teaspoon of water, it would be just as light. But if you could somehow fly to a white dwarf and scoop up a single teaspoon of its crushed, deeply compressed material, bringing it back down to Earth, that single spoonful would weigh as much as a fully loaded freight train or a herd of several massive elephants. It is matter pushed to its absolute physical limit. The atoms themselves have been crushed together so violently that the normal, empty spaces that exist inside all matter have been entirely squeezed out. The material is packed shoulder to shoulder, locked in a rigid, unyielding state. It is as solid and permanent as anything in the universe can possibly be. And yet, despite the fact that the fire has completely gone out, a white dwarf glows. It shines with a fierce, brilliant, piercing white light. If there is no fusion happening, you might naturally wonder where this light is coming from. The answer is simply residual heat. Consider a heavy cast iron skillet resting on a kitchen stove. If you turn the burner up to high and let the iron sit there for an hour, it absorbs a tremendous amount of thermal energy. When you finally turn the stove off, the flame is gone, but the skillet does not become instantly cold. Because iron is incredibly dense, it holds on to that heat, remaining dangerously hot to the touch long after the fire is out. Or imagine a heavy, solid wooden log in a campfire. Long after the bright yellow flames have died away, the thick, heavy ember in the center of the pit continues to glow with a blinding, white-hot intensity, radiating warmth out into the chilly night air. The white dwarf is the ultimate cosmic ember. It was forged in the unimaginably fierce, 10 million degree fires of a collapsing stellar core. Because it is so unimaginably dense, it holds on to that heat with incredible stubbornness. Furthermore, space itself acts like a colossal, perfect thermos. Down here on Earth, things cool off relatively quickly because the air around them carries the heat away. If you set a hot cup of coffee on a table, the cooler air in the room sweeps over the mug, stealing the heat until the coffee matches the temperature of the room. But space is a complete vacuum. There is no air, no breeze, and no material to conduct the heat away. The only way for the white dwarf to cool down is to slowly, quietly radiate its energy out into the darkness as light. Because of this deep insulation, a white dwarf takes a staggeringly long time to cool off. It takes billions upon billions of years for the heavy, glowing sphere to gradually lose its heat. It will slowly transition from a blinding white to a softer yellow, then to a deep, smoldering red, and finally, over an incomprehensible stretch of time, it will fade to black. In fact, this cooling process is so incredibly slow that the universe itself is not yet old enough for a single white dwarf to have completely cooled down. Every single white dwarf that has ever been created since the dawn of time is still out there right now, still glowing in the dark, still holding on to the ancient heat of its birth. When they eventually do lose the very last of their warmth, perhaps hundreds of billions of years from now, they will become what we call black dwarfs. They will be cold, silent, invisible spheres drifting endlessly through the void. Because they are composed largely of carbon that has been crushed under unimaginable pressure, it is very likely that the interiors of these cooled stars will crystallize. They will become colossal, Earth-sized diamonds, perfectly hidden in the pitch black of deep space. It is a deeply peaceful, dignified retirement for a star that spent billions of years lighting up its corner of the galaxy. So what does this actually mean for stars that are much larger and heavier? That's what we'll gently explore next. For a medium-sized star, like our own steady sun, we saw that the end of its life is a slow, quiet exhalation, leaving behind a glowing ember to peacefully cool in the dark. But the universe is home to stars that dwarf our sun in scale, massive, brooding giants that weigh 10, 20, or even 50 times as much as our local star. Because of their sheer, overwhelming mass, the rules of their existence are fundamentally altered. They do not get to fade away quietly. Their lives are characterized by immense pressure, and their endings are among the most incredibly violent, spectacular events in the cosmos. To understand why these massive stars end so dramatically, we have to look at how they live. You might naturally assume that because a star is massive, it has much more fuel, and therefore it should live much longer. But the reality is the exact opposite. Because these giant stars are so intensely heavy, their gravity presses upon their cores with staggering force. To fight back against that monumental inward pressure, the star has to burn through its fuel at a ferocious, almost reckless pace. If our sun is like a small, highly reliable car that can cruise steadily for days on a single tank of gas, a massive star is like a heavy, roaring freight train, constantly shoveling coal into its furnace as fast as physically possible just to keep moving forward. Because of this ravenous appetite, a massive star burns through its hydrogen in just a few million years, a mere blink of an eye in cosmic time. When the hydrogen runs low, the core shrinks and heats up, just as it does in smaller stars. But because this star is so remarkably heavy, the crushing weight pushes the core to temperatures of hundreds of millions of degrees. At these extreme temperatures, the star can start fusing heavier and heavier elements to keep its central fire going. It fuses helium into carbon, carbon into oxygen, oxygen into neon, and neon into silicon. The inside of the massive star becomes beautifully layered, much like the concentric rings of an ancient tree or a set of perfectly fitted wooden nesting dolls. Each layer is burning a different element, all surrounding a blistering, continually shrinking core. But this frantic, desperate burning cannot continue indefinitely. Eventually, the star reaches a profound and fatal roadblock: iron. Deep in the very center of the star, the immense pressure forces silicon atoms to fuse together to create iron. For millions of years, every time the star fused lighter elements together, the process released a burst of outward energy. That released energy was the vital, pushing force that held the heavy star up against the crush of its own gravity. Iron, however, is uniquely stubborn. It is the end of the line. Fusing iron does not release energy. Instead, it absorbs energy. It acts like a massive sponge, soaking up the heat of the core. Suddenly, the engine that has kept the star alive completely stalls. Imagine an enormous, heavy suspension bridge, built of solid stone and heavy steel, resting entirely on one single, central pillar. For years, that pillar has held up millions of tons of weight without shifting. Now, imagine if that pillar simply vanished in the blink of an eye. The bridge wouldn't slowly sag. it would instantaneously collapse under its own staggering weight. That is exactly what happens inside a massive star. The moment iron begins to rapidly build up in the core, the outward pressure drops to zero, the central pillar vanishes. With nothing left to hold it back, gravity wins an absolute, catastrophic victory. The entire weight of the massive star, millions of Earth's worth of gas and plasma, crashes inward at a significant fraction of the speed of light. All of that falling outer material slams violently into the solid iron core and rebounds, creating a shockwave of unimaginable power. This rebounding shockwave blasts the star entirely apart in a colossal explosion called a supernova. The sheer violence of a supernova is difficult for the human mind to fully grasp. In a single, blinding fraction of a second, the exploding star releases more energy than our sun will produce in its entire billions of years-long lifetime. The flash of light is so fiercely bright that it can temporarily outshine every other star in its entire galaxy combined. But this explosion is not just a destructive ending. It is a vital, creative forge. The extreme heat and pressure of the supernova are so incredibly intense that they force atoms to fuse past the iron roadblock, creating the heaviest materials in the universe, elements like gold, silver, platinum, and uranium. All of these heavy elements, along with the carbon and oxygen from the star's outer layers, are violently blasted out into the dark, sweeping across the cosmic ocean. The calcium in your teeth, the iron in your blood, and the heavy gold in a wedding ring were all forged in the heart of an exploding, dying star. We are all, quite literally, made of stardust. As the blinding flash of the supernova slowly fades over the following months, leaving a beautiful, sprawling cloud of glowing gas drifting through the galaxy, something remains behind in the very center of the destruction. The iron core that triggered the collapse has been crushed to an impossible density. The inward pressure was so severe that the very structure of the atoms was shattered. The electrons were violently smashed directly into the protons, leaving nothing behind but a tightly packed sphere of pure neutrons. We call this remnant a neutron star. It is an object that stretches the limits of physics. A neutron star packs the entire mass of our sun, and sometimes more, into a perfectly smooth, dark sphere that is barely 10 or 12 miles across, roughly the footprint of a single earthly city. If you thought a white dwarf was incredibly dense, a neutron star defies reason entirely. If you could somehow take the entire human population of the Earth, all 8 billion of us, and crush all of that physical matter down without losing a single ounce of its weight, you could fit the entire human race into a volume the size of a single sugar cube. That is the staggering density of a neutron star. Because it collapsed so quickly, a neutron star also spins at breathtaking speeds. Imagine a figure skater pulling her arms tightly into her chest to spin faster on the ice. The star does the exact same thing, pulling millions of miles of slow rotation down into a 12-mile sphere. Some neutron stars rotate hundreds of times every single second, casting invisible beams of intense magnetic energy out into the dark, humming like cosmic lighthouses in the deep. They are silent, heavy, and wildly energetic monuments to the most powerful events in the dark. Let's set that idea down now, fully formed, and let our attention drift toward the most extreme objects in the universe. We just imagined the staggering, almost incomprehensible density of a neutron star, where the entire mass of a sun is crushed down into a sphere no larger than a city. In that extreme environment, gravity has squeezed the atoms so tightly that they shatter, leaving only the fundamental building blocks, the neutrons packed shoulder to shoulder to hold up the immense weight of the dying star. But what happens if the original star was even heavier? What happens if the star was 30, 40, or even 50 times as massive as our own sun? When a giant of that scale exhausts its fuel and its iron core inevitably collapses, the inward crush of gravity is so overwhelmingly powerful that even the tightly packed neutrons cannot withstand the pressure. They fail. And when they fail, there is absolutely no physical force left in the universe that can stop gravity from pulling everything completely inward. Gravity wins an absolute, terrifying, and ultimate victory. Picture that 12-mile-wide neutron star, already containing the weight of 1,000,000 Earths, being crushed down even further. Imagine it shrinking to the size of a baseball, then down to the size of a single grain of sand, and then it simply keeps going. It shrinks until it has absolutely no physical dimensions left at all. All of that monumental mass, the entire remains of a giant star, is concentrated into a single, microscopic point in space with zero volume. Physicists call this point of infinite density a singularity. It is a place where our normal understanding of reality and the very laws of physics that govern our daily lives simply fold up and cease to make sense. Because all of that staggering mass is packed into an infinitely small point, the gravitational pull immediately surrounding it becomes unimaginably fierce. To understand how this shapes the space around it, we need to quietly explore a foundational rule of physics known as escape velocity. We can build this idea together from the ground up, using something deeply familiar. Imagine standing in a quiet park on a summer afternoon, tossing a baseball straight up into the air. The moment the ball leaves your hand, the Earth's gravity begins pulling on it. It slows down, stops for a brief fraction of a second in midair, and falls right back down into your palm. If you throw it harder, with more energy, it will travel much higher before the gravity eventually overcomes its momentum and pulls it back. But there is a very specific, critical speed at which you could throw that ball so fast that the Earth's gravity could never slow it down enough to reverse its direction. For our planet, that speed is roughly 25,000 miles per hour. If the ball leaves your hand at that exact speed, it will travel out into the dark of space and never return. This relationship between the sheer mass of an object and the speed required to break free from its gravitational grip is a fundamental law. The heavier and more dense the object, the faster you have to move to escape it. Now, return to that microscopic point of infinite density in deep space. Because the mass is so heavily concentrated, as you get closer to the singularity, the required escape velocity rises incredibly sharply. It climbs to millions of miles per hour and then to hundreds of millions. Eventually, at a certain distance from the singularity, the escape velocity becomes perfectly equal to the speed of light itself. Think back to our earlier realization that the speed of light is the absolute, unbreakable speed limit of the entire universe. Nothing can travel faster. So, if the gravity is pulling so hard that you would need to travel faster than light just to escape it, it means that absolutely nothing can ever leave. You can visualize this by imagining you are paddling a small kayak on a wide, slow-moving river that is flowing steadily toward a massive, towering waterfall. As long as you are far upstream, the current is gentle. You can easily turn your boat around, paddle against the flow, and head back to the safety of the shore. But as you drift closer and closer to the edge of the falls, the water begins to speed up. The current grows stronger and more insistent. Eventually, you will cross a very specific, invisible line in the water. At this exact line, the river is flowing forward toward the edge at exactly the maximum speed you are capable of paddling backward. Even if you paddle with all your strength, giving it everything you have, you will remain perfectly stationary against the shore for a fleeting moment before inevitably being swept over the edge. For a black hole, this invisible line of no return is called the event horizon. It is deeply important to realize that the event horizon is not a physical surface. It is not made of rock or ice or thick gas. You could not land a ship on it, and you could not reach out and touch it. It is simply a mathematical boundary, an invisible sphere in empty space completely surrounding the singularity. Once anything, a wandering asteroid, a drifting cloud of gas, or even a pure particle of light crosses this boundary, it is swept irreversibly inward. Because not even light can paddle fast enough to escape the current of gravity at the event horizon, the object is completely dark to us. If you were to shine a brilliant flashlight directly outward from just inside that boundary, the beam of light would be dragged backward, falling down into the singularity just like our paddler caught in the waterfall. No light ever leaves, which means no information ever leaves. Looking at a black hole is looking at a perfect, absolute absence of light. It is a quiet, spherical shadow, an invisible rip in the fabric of space itself. It is very common to imagine black holes as colossal, cosmic vacuum cleaners, aggressively roaming through the galaxy, sucking up everything in their path. But they are actually incredibly patient and entirely passive. If we were to magically replace our own sun with a black hole of the exact same mass, the Earth would not be suddenly sucked in. Our planet would continue to follow its exact same orbit, gliding along the exact same path it follows today, completely undisturbed by the change, though our world would quickly become terribly cold and dark. A black hole only pulls you in if you wander too close and accidentally stumble across the event horizon. Otherwise, it simply rests in the dark, waiting. If they are completely invisible, you might naturally wonder how we even know they are there. We find them by looking at how their immense gravity influences the things around them. When a star happens to orbit a little too close to a black hole, the fierce gravity pulls at the star's outer layers of gas, unraveling it slowly, like pulling a loose thread on a sweater. This stolen gas spirals inward toward the event horizon, forming a wide, flattening disk, much like water swirling around a drain. As this gas swirls closer and closer to the edge of the event horizon, moving at nearly the speed of light, it bumps and rubs against itself. The friction heats the gas to billions of degrees. This swirling disk glows with a blazing, fierce energy, radiating intense X-rays and blinding light. It acts like a brilliant, chaotic neon sign in the dark, pointing directly to the perfectly quiet, perfectly invisible shadow resting in its center. It is a beautiful, violent paradox. The darkest objects in the universe are often wrapped in the brightest, most luminous displays of light. A moment ago, we ended with the idea of massive stars shaping the space around them. Let's pick up that thread right where we left it and zoom out to see how all these stars are organized. When you picture the universe in your mind, it is very natural to imagine a vast, infinite room filled with a perfectly even, uniform fog of stars, stretching out endlessly in every direction. We tend to think of space as a uniformly mixed soup, where everything is scattered randomly and equally. But the cosmos is far more structured and far more elegant than a simple, random scattering. To understand this structure, imagine looking at a satellite photograph of the Earth taken late at night. You do not see a perfectly even blanket of city lights covering every inch of the globe. Instead, you see vast, profound stretches of absolute blackness, the deep oceans, the sweeping deserts, the quiet, empty mountain ranges. And separated by those vast tracts of dark wilderness, you see intensely bright, glowing clusters of light. These are our cities and metropolises. Human beings naturally gather together in concentrated hubs, bound by roads and communities, leaving immense stretches of empty land between them. Gravity organizes the universe in the exact same way. Stars do not drift alone in the endless void. They gather together in unimaginable numbers, bound by their collective gravitational pull, forming colossal, glowing cities of light. We call these grand cosmic cities galaxies. Our own planet, our sun, and every single star you have ever seen with your naked eye all belong to one specific, magnificent city. Our galactic home is called the Milky Way. It is a sprawling, rotating metropolis containing somewhere between 100 billion and 400 billion individual stars. Just pausing to hold that number in your mind can feel overwhelming. If you were to try and count every single star in our galaxy, one by one, counting one star every second, without ever stopping to sleep or eat, it would take you over 3,000 years to finish. If you could somehow detach yourself from the Earth, fly millions of light years straight up into the dark, and look down at the Milky Way from above, you would be treated to one of the most breathtaking shapes in nature. It does not look like a chaotic, random blob. It looks like a majestic, perfectly balanced, glowing pinwheel. At the very center of this pinwheel is the galactic core. You can think of this as the bustling, heavily crowded downtown district of our city. It is an intensely bright, tightly packed, spherical bulge of ancient stars. In this central hub, the stars are packed so closely together that the night sky on a planet there would be brilliantly illuminated, glowing with the light of a million suns. And resting quietly in the exact, dead center of this glowing downtown is a supermassive black hole. This is the quiet, invisible anchor of our entire galaxy, a gravitational heavyweight millions of times more massive than our Sun, quietly holding the sprawling city together as it spins. Winding gracefully outward from this bright, dense center are the spiral arms. Imagine taking a cup of dark coffee and slowly pouring in a stream of heavy cream, stirring it gently with a spoon. You would see sweeping, curved ribbons of cream spiraling out from the center. The Milky Way's arms look exactly like this, but they are forged from billions of stars, vast drifting nebulae, and long sweeping trails of interstellar dust. These arms are the industrial zones of the galaxy, the places where new stars are actively being born in the cold, dark clouds we explored earlier. But our solar system is not located anywhere near the bustling, chaotic center of the galaxy, nor are we resting on the very outermost fading edge. We live in the galactic suburbs. We are situated about halfway between the glowing core and the dark outer rim, nestled quietly on the inner edge of one of the smaller, branching spiral arms. This location is incredibly fortunate for us. If our Sun were located in the deep center of the galaxy, the radiation from the dense cluster of ancient stars and the frequent, violent supernovas would be too intense for fragile atmospheres and delicate oceans to survive. It would be a beautiful but deeply hostile place to try and build a living world. Instead, we reside in a quiet, peaceful cul-de-sac of the galaxy. Our cosmic neighborhood is stable, calm, and relatively empty, giving our Sun the billions of years of uninterrupted peace necessary for a small blue planet to develop liquid oceans and eventually life. You might wonder, if we live inside this sprawling, flat pinwheel of stars, what does it look like from the inside? Why do we call it the Milky Way? Think about standing inside a very large, flat, circular forest. If you look straight up or straight down, you only see a few trees, and beyond them, the open sky. But if you look straight ahead, horizontally through the woods, your line of sight passes through thousands and thousands of tree trunks, overlapping one another until they form what looks like a solid wall of wood. The Milky Way galaxy is very flat, much like a vinyl record or a heavy pancake. Because we live inside that flat disk, when we look out into the night sky, most directions offer us a relatively clear, unobstructed view into the deep, empty universe. But when we look horizontally, directly along the flat plane of the disk itself, our line of sight passes through the thickest, most densely packed cross-section of the entire galaxy. We are looking through the billions of overlapping stars that make up the spiral arms. From the surface of the Earth, this sheer volume of distant stars blends together, appearing not as individual points, but as a soft, glowing, cloudy band of light stretching entirely across the dark sky. To the ancient observers who had no telescopes, it looked as though someone had spilled a trail of sweet milk across the heavens. That simple, beautiful observation gave our magnificent city its name. When you find yourself in a truly dark place and you see that pale, glowing river of light arcing overhead, you are actually looking edgewise into the vast, spinning disk of your own galactic home. And it is, in fact, spinning. Just as the moon orbits the Earth and the Earth orbits the Sun, our entire solar system is orbiting the massive, bright center of the Milky Way. Gravity commands motion at every scale of the universe. The Sun, carrying the Earth and all the other planets along with it, is hurtling through space, tracing a massive circle around the galactic core. Even though we are moving at a staggering speed of over 500,000 miles per hour, the galaxy is so unimaginably large that it takes us a very long time to complete a single trip. It takes the Sun roughly 230 million Earth years to make just one full circle around the Milky Way. This sweeping journey is called a galactic year. To put that profound timescale into perspective, the last time our planet was in this exact spot in the galaxy, human beings did not exist. The very first dinosaurs were just beginning to walk across the surface of the Earth. We are constantly in motion, participating in a grand, silent carousel that has been turning gracefully in the dark for over 10 billion years. We are safe in our quiet suburb, drifting along our majestic path, completely sheltered by the sweeping arms of our cosmic home. Before we rest here, let me whisper where we're headed next, not to rush, but to plant a seed about the vastness that exists between these grand cities of light. For a very long time, humanity held a quiet, comforting belief about the limits of reality. Up until about a century ago, the greatest minds on Earth believed that the Milky Way, our grand, spinning pinwheel of billions of stars, was the entire, complete universe. It was a massive structure, to be sure, but it was contained. It was a single, solitary island of light suspended in an infinite, dark, and empty ocean. There was a profound sense of coziness in that thought. We knew our cosmic city. We could map its sweeping arms, and we believed that once you reached the edge of our galaxy, there was simply nothing else left to find. But as the years passed, our vision grew sharper. Astronomers spending long, freezing nights on the peaks of high mountains, peering through the glass lenses of new, massive telescopes, began to notice something strange. Scattered between the familiar, sharp pinpricks of local stars, they saw faint, glowing smudges of light. At first, they naturally assumed these were just small, cloudy nurseries of gas resting quietly within our own galaxy. They called them spiral nebulae, believing them to be close and relatively small. Then, the true scale of the universe was revealed, and it fundamentally shattered our understanding of our place in the dark. By carefully measuring the faint, pulsing light coming from these smudges, we realized a staggering truth. They were not small clouds of gas inside our galaxy. They were entirely separate, colossal galaxies of their own, resting at distances so incredibly vast that it almost defies human comprehension. Those tiny, faint smudges were actually island universes, each one containing hundreds of billions of their own stars, their own sweeping spiral arms, and their own nebulae, all reduced to a tiny blur simply because they were so agonizingly far away. Suddenly, the universe multiplied. We now know that if you were to pick a tiny, seemingly empty patch of the darkest night sky, a patch no larger than the size of a grain of sand, held at arm's length and stared deep into it, you would find thousands upon thousands of galaxies hiding in that tiny speck of dark. There are hundreds of billions of galaxies out there, scattered across the deep, silent cosmic ocean, stretching as far as our instruments can possibly see. The space between these galaxies is known as the intergalactic void. If the galaxies are bustling, brilliantly lit metropolises, the intergalactic void is the deep, dark, silent ocean that separates the continents. It is the truest emptiness in nature. If you were to find yourself drifting in the space between galaxies, the darkness would be absolute. The nearest star system wouldn't be a few light years away, it would be millions of light years away. You would be wrapped in a profound, freezing silence, untouched by the warmth of any sun. But this massive, unimaginably vast ocean of space is not a static, still canvas. It is not a fixed stage upon which the galaxies simply rest. The universe is engaged in a grand, sweeping motion. The universe is expanding. To understand this concept, we have to let go of the way we normally think about movement here on Earth. When a car drives down a highway or a bird flies through the sky, they are moving through space. The space itself stays perfectly still, and the object travels from one side of it to the other. But the expansion of the universe is entirely different. The galaxies are not firing massive rocket engines and flying through the void. Instead, the very fabric of space itself is quietly, continuously stretching. Imagine you are in a warm, comfortable kitchen, baking a loaf of raisin bread. You have just finished kneading the soft, heavy dough, and you have folded a handful of dark, sweet raisins into the mix. You place the dough in a warm spot on the counter, cover it with a soft towel, and let it rest. Slowly, the yeast begins to work, and the dough begins to rise. It expands outward in every single direction, swelling and puffing up. If you were to imagine yourself as one of those tiny raisins sitting inside the dough, what would you see? As the dough rises, every single other raisin in the loaf would appear to be moving away from you. The raisin an inch to your left slowly drifts further to the left. The raisin an inch to your right drifts further to the right. But neither you nor your neighbors are actually swimming or moving through the dough. You are all just sitting perfectly still in your own little pockets. It is the dough itself, the space between you, that is expanding, stretching the distances wider and wider. The galaxies are the raisins, and the empty vacuum of space itself is the dough. Space is quite literally swelling, and because the fabric of space is stretching everywhere all at once, there is no center to this expansion. No matter which galaxy you are living in, if you look out into the dark, it looks as though every other galaxy in the entire universe is drifting away from you. We can actually measure this stretching by looking at the light arriving from these distant cosmic cities. Have you ever been lying in bed at night, completely still, and heard a train blow its whistle as it speeds past your town? As the train is moving toward you, the sound waves are bunched up, and the whistle sounds higher in pitch. But the exact moment the train passes you and begins moving away, the pitch drops. It stretches out into a lower, deeper, mournful tone. This is called the Doppler effect. Light behaves in the exact same way, just with color instead of sound. As the galaxies drift away from us, the light they emit is literally stretched out by the expanding space. In the spectrum of light, longer, stretched-out waves appear red. This is known as redshift. When we look at distant galaxies, their light has been gently stretched into longer, softer, redder wavelengths. It is the visual equivalent of that distant train whistle dropping in pitch as it disappears into the dark, a visual echo of their silent departure. Because it is the space between the galaxies that is stretching, we discover a beautiful, logical rhythm to this expansion. Think back to the raisin bread. If there is 1 inch of dough between you and your neighbor, that 1 inch of dough expands. But if there is a raisin on the far side of the loaf, with 10 inches of dough between you, there is much more dough doing the stretching. Because of this, the raisin further away appears to be moving away from you much faster. The same is true for the cosmos. The further away a galaxy is from us, the more stretching space there is between our world and theirs, which means it appears to be receding at a much faster speed. It is a steady, silent, drifting apart on a cosmic scale. There is no turbulence in this motion, no jarring shifts. It is just a relentless, peaceful stretching of the dark, carrying the grand cities of light further and further into isolation. The universe is exhaling a breath it has been letting out for billions of years, slowly expanding the canvas of reality into something ever more vast and ever more quiet. And with that understanding quietly in place, we're naturally led to ask how this grand expansion began in the first place. If we know that the universe is steadily expanding outward, carrying the grand cities of light further and further apart, we can use our imagination to do something profoundly simple. We can conceptually run the clock backward. Imagine watching a long, sweeping film of the cosmos, and then gently pressing the rewind button. The silent drifting apart of the galaxies would smoothly reverse. If things are moving away from each other today, then logic tells us they must have been closer together yesterday. If we rewind the film a million years, the galaxies are drawn a little bit nearer to one another. The empty, freezing oceans of intergalactic space become a little narrower. If we continue to let the film run in reverse, rewinding through billions of years of cosmic history, the universe becomes increasingly crowded. The vast distances between the galaxies vanish entirely. Eventually, the galaxies themselves lose their beautiful spiral shapes, their stars merging and blending as the space containing them shrinks. The universe becomes incredibly dense, and as a result, it becomes incredibly hot. If you compress any physical material, just like squeezing the air tightly inside a bicycle pump, it heats up. The universe is no exception. As we rewind the clock all the way back, nearly 14 billion years into the deep past, we arrive at the absolute limit of our physical understanding. We reach a moment where the entire observable universe, every single star, every galaxy, every drifting nebula, and all the empty space in between was compressed into a single, intensely hot, infinitely dense point. The moment when this single point began to swell outward is what we call the Big Bang, but the name itself is actually a bit misleading. When we hear the phrase Big Bang, it is incredibly natural to picture a colossal explosion. We tend to imagine a massive firecracker going off in the middle of a vast, empty, dark room, sending pieces of shrapnel flying out into the pre-existing space. But the universe did not explode into space. There was no dark room waiting to be filled. Instead, the Big Bang was an explosion of space itself. To picture this, imagine the surface of a small, uninflated balloon. Now, imagine drawing little dots all over the rubber with a marker. As you blow air into the balloon, the rubber stretches, and every single dot moves further away from every other dot. The dots are not sliding across the rubber. The rubber itself is expanding beneath them. Now, apply that to the cosmos. At the very beginning, all of space, all of time, and all of the energy that would eventually become the stars and planets were folded up into that initial, unimaginably hot state. And then, space simply began to stretch. It expanded rapidly, swelling outward in every possible direction, carrying the raw energy of creation along with it. In its earliest moments, the universe looked absolutely nothing like the quiet, dark, starlit expanse we gaze up at today. Because everything was still so densely packed together, the heat was absolute and overpowering. The universe was filled with a blinding, blistering soup of raw energy. It was so chaotic and so incredibly hot that simple atoms could not even form. If a proton and an electron tried to join together to make a gentle atom of hydrogen, the furious, boiling energy of the universe would instantly smash them apart again. During this time, the universe was essentially a thick, glowing, opaque fog. Imagine trying to drive your car down a highway in the middle of a deeply dense, white fog. You turn your headlights on, but the light doesn't travel down the road. Instead, it hits the thick water droplets in the air and scatters, bouncing right back at you, illuminating nothing but the wall of fog itself. The early universe was exactly like this. Light particles were trapped. They could not travel in a straight line without immediately crashing into a frantic, high-speed electron, bouncing off in a random direction. Because light could not move freely, the universe was entirely opaque. It was a blinding, glowing wall of heat. But as the universe continued to expand, it naturally began to cool down. Think about a pressurized can of air you might use to clean a computer keyboard. When you press the trigger and the compressed gas expands outward into the room, the metal can becomes freezing cold in your hand. Expansion causes cooling. For roughly 380,000 years, the fabric of space stretched, and the blistering heat of the cosmos slowly, steadily dropped. Eventually, the temperature reached a critical, quiet threshold. The universe was finally cool enough for the frantic electrons to slow down. The protons reached out, grabbed the electrons, and held onto them. The very first atoms of hydrogen and helium were officially formed. When this happened, the dense, chaotic fog of loose electrons vanished. The blinding walls simply evaporated. For the very first time in cosmic history, the universe became beautifully, perfectly transparent. And all of that trapped light, the brilliant, blazing radiation that had been bouncing around blindly for hundreds of thousands of years, was suddenly free. It burst forward, traveling in straight lines across the newly cleared expanse of space. This breathtaking release of light filled the entire universe simultaneously, a magnificent flash of creation washing over everything at once. That light has been traveling through the absolute dark for over 13 billion years, and incredibly, it is still traveling today. It is washing over the Earth, passing through your room, and resting gently against your skin right at this very moment. But if this flash of light was so brilliant, why is the night sky dark? Why can't we see it? The answer brings us perfectly back to the expanding dough of our cosmic loaf of bread. As that ancient, brilliant light traveled through the void for 13 billion years, the space it was traveling through was continuously stretching, and as space stretches, it stretches the light along with it. When the light was first released, it was a searing, high-energy, visible light, glowing with an intense, fiery orange and white heat. But as the universe expanded, the tight, energetic waves of that light were pulled out, becoming longer and lazier. They were stretched so far that they shifted completely out of the visible spectrum. Our human eyes can no longer perceive them. The light stretched into the infrared, and then continued stretching until it became what we call microwave radiation. Today, this ancient flash of light is known as the cosmic microwave background. It is a faint, invisible hum of energy that completely fills every single corner of the sky, in every possible direction. It does not come from any specific star or any particular galaxy. It comes from everywhere at once, because it is the lingering echo of the universe itself, from a time when everywhere was in the exact same place. It is the ultimate, quiet remnant of the beginning. You can think of it like the gentle, comforting warmth of a large kitchen oven long after it has been turned off. The blazing fire is gone, the baking is finished, and the room is dark. But if you hold your hand near the cast iron, you can still feel the soft, ambient heat radiating into the quiet room, proving that the fire was once there. If you remember the old heavy tube televisions from decades ago, the ones with the thick glass screens and the twisting dials, when you turned the dial to a channel that had no station broadcasting, the screen would fill with a chaotic, buzzing black and white static, often called snow. A small percentage of that static, the actual interference being picked up by the metal antenna on top of the television, was the physical interaction of the cosmic microwave background. Without even knowing it, sitting in your living room, you were watching the cooling echo of the Big Bang tapping softly against the glass of your television screen. It is a deeply peaceful thought. The universe began in unimaginable heat and chaotic density, but it has spent the last 14 billion years stretching out, cooling down, and making room for grand galaxies, quiet planets, and eventually, us. We are continuously bathed in the ancient light of our own creation, cooled to a gentle, invisible whisper that surrounds us as we sleep. So what does this actually mean for us, sitting here in the quiet dark? That's what we'll gently explore next. We have traveled an immense distance together tonight. In our minds, we have stepped off the solid ground of our silently turning Earth and drifted past the quiet, rusted deserts of Mars. We have navigated the empty, freezing gaps of the asteroid belt to witness the swirling, painted storms of Jupiter and the delicate, icy halo of Saturn. We have stood at the very edge of the solar system, where the sun is just another faint star in the black, and we have plunged into the deep, interstellar void, watching ancient nebulae slowly pull themselves together to ignite new suns. We have watched giant stars collapse and forge the heavy elements of reality, and we have traced the sweeping, majestic arms of our own Milky Way. Finally, we rode the very fabric of expanding space all the way back to the ancient, cooling echo of the beginning of time. When you hold all of this vastness in your mind at once, the hundreds of billions of galaxies, the trillions of wandering stars, the crushing black holes, and the endless, stretching dark, it is incredibly easy to feel small. It is completely natural to look up at a clear night sky, comprehend the sheer, staggering scale of the cosmos, and feel as though human beings are entirely insignificant. We can sometimes seem like nothing more than a fleeting whisper on a tiny speck of pale blue dust, adrift in a universe that is overwhelmingly large and deeply indifferent to our existence. But that feeling of insignificance relies on a quiet misunderstanding. It assumes that you are somehow separate from the universe, just a tiny, isolated observer sitting on the outside and looking in through a cold window. The truth of your existence is far more intimate and profoundly more beautiful. You are not separate from the universe at all. You are a direct, physical extension of it. Think back to the colossal, massive stars we watched exploding in the dark. We saw how their intense, crushing cores acted as the ultimate cosmic furnaces, fusing the simple, lightweight hydrogen of the early universe into heavier, more complex things. For billions of years after the cosmos began, the universe contained almost nothing but hydrogen and helium gas. There was no carbon, no oxygen, no nitrogen, and no iron. There were absolutely no ingredients to make a solid rocky planet, let alone a living, breathing person. Those heavy elements had to be forged. They had to be baked in the unimaginably fierce fires of giant stars. And when those massive stars finally reached the end of their lives and violently exploded in brilliant supernovas, they did not just disappear into the void. They cast those newly forged heavy elements out into the deep, freezing oceans of space. That scattered stardust drifted quietly for eons. It mixed with the ancient, wandering clouds of gas. It was swept up into new, spinning nebulas, and eventually, gravity gently pulled it all together to form the rocky crust of the Earth, the deep, salty water of our oceans, and the very air we breathe. That exact same stardust was pulled together to form you. The universe recycled its greatest, most violent triumphs into the quiet shape of a human being. Consider the blood quietly moving through your veins right now, steadily carrying oxygen from your lungs to the tips of your fingers and toes. The molecule that makes your blood red, the very thing that binds to the oxygen and keeps you alive, is built around an atom of iron. Every single atom of iron in your bloodstream was forged in the crushing core of a dying star that existed billions of years before the Earth was even formed. That star had to collapse, explode, and scatter its heart across the dark, just so that iron could eventually find its way into your body, allowing you to take the slow, steady breath you are taking right now. The calcium that gives strength to your bones, holding your frame together, was created in that same stellar fire. The oxygen filling your lungs, the carbon that forms the foundation of every single cell in your body, they are all ancient. You are quite literally a collection of stardust, gathered together for a brief, beautiful moment in time. When you realize this, the vastness of space no longer feels cold or isolating. The universe is not a distant, empty room that you happen to be standing inside. It is your deepest ancestry. You are made of the exact same material as the sweeping spiral arms of the galaxies and the glowing clouds of the nebulae. You are the universe. And you are a very special part of it. For nearly 14 billion years, the cosmos has been blindly expanding, swirling, burning, and cooling. It has been engaged in a magnificent, silent dance, driven entirely by gravity, pressure, and time. But through a long, miraculous chain of events, on a quiet blue planet orbiting a steady yellow sun, a tiny fraction of that cosmic material woke up. It organized itself into a mind. It opened its eyes. You are the universe experiencing itself. When you stand in a quiet field and look up at the stars, it is the universe looking back at its own light. When you try to understand the spinning of the planets or the invisible stretching of space, it is the cosmos trying to understand its own magnificent architecture. You are the consciousness of the dark. There is a tremendous peace in that realization. It means that your life, with all its quiet moments, its daily routines, its gentle hopes, and its resting hours, is an integral part of the grand story of reality. Your existence is a cosmic triumph. The universe spent over 13 billion years preparing the stage, forging the materials, and setting the planets in motion, all so that you could be here, resting softly in the dark, breathing quietly, and holding the thought of the stars in your mind. Let the weight of that connection settle over you like a warm, heavy blanket. Feel the steady rhythm of your heartbeat, and know that it is powered by the ancient fires of the cosmos. Feel the gentle pull of the Earth's gravity holding you safely in your bed, the exact same ancient force that holds the moon in its orbit and guides the spinning galaxies through the void. You belong here. You are exactly where you are supposed to be. As you drift deeper into rest, you can let go of the immense scales and the staggering distances. You do not need to hold the whole universe in your mind anymore. You can let the spinning planets slow down. You can let the roaring fires of the stars gently fade into soft, comforting embers. You can let the expanding fabric of space settle into a profound, completely undisturbed stillness. And so we come to the end of our time with the cosmos tonight, not an ending, really, but a place to rest. You've let these ideas settle beside you as you slept, and they'll be here whenever you return. No tests, no grades, just a quiet sense that you understand a little more than you did before, resting peacefully under a sky you now know so well. You have journeyed to the very edge of time and space, and now you have returned safely to your own quiet room. The stars will keep watch outside your window, tracing their ancient silent arcs across the dark, while the earth gently turns you toward tomorrow's dawn. Until then, sleep well and carry nothing but that.